zooming in. There we go. Okay. And so we've used it in regards to simple linear regression and multiple variable regression. For is there a relationship between our input and output variables? In simple linear, it's is there a relationship between them? Multiple regression we're testing, do all of them affect the relationship, or is there at least one that doesn't? Or sorry, I think that was backwards. Do they all not affect, or at least one that does? Yeah, they all not affect, or is there at least one that does? We have attached the name ANOVA to this, but really it's this testing of regression, testing of is there a relationship. ANOVA is, I gave that wording, stands for analysis of variance, and it's comparing variations. We have ANOVA, the F statistic, takes the ratio of the average explained variation divided by the average unexplained variation. And so if more of it is explained than unexplained, there's a relationship. This is comparing from specific sources with the variation among individuals who should be similar. In particular, ANOVA is testing whether several populations have the same means. So when we're doing it with regression, there was that picture. I can probably find it pretty quickly. In simple linear regression, we were comparing the mean responses, and they all had this standard spread. So we are ultimately comparing means, comparing how far apart the sample means are with how much variation there is within the sample. So when we're talking about one-way ANOVA, we're now taking a categorical variable, a treatment type, against a quantitative output. So categorical input, what treatment are they receiving against a quantitative output? So we're comparing means of 3 or more groups. So like comparing the mean blood pressure when 3 different diets are being tested in our samples. Comparing test scores when 4 different teaching methods are being used. Comparing reaction times under certain different conditions. So we're comparing 3 or more means where the response is quantitative and that explanatory is that categorical. So before we could have done t-tests, but the most a t-test could compare was 2 means. Section 7.2 was what if I want to do t-tests and compare means of 2 groups? ANOVA tests all the groups at once to see, are there a difference between the means? Is the variation enough to determine if those differences in the means are statistically significant? So when we are using this ANOVA, the main question is, are the differences between the group means larger than what we would expect from random variation? The hypotheses, the null hypothesis is all population means are equal. The alternative is not all the population means are equal. At least one of them is different. One of them is giving a different result. Or at least one is giving a different result. So the means between the three groups or more groups are all the same for the null, the alternative. At least one of these is different. So back to these examples, comparing mean blood pressure across three different diets, we're testing, is that blood pressure the same across all three, or is there at least one that's giving that different blood pressure? I would assume trying to improve. Test scores are all four different teaching methods, resulting in students getting about the same test score with random variation accounted for. Or is there one teaching method that's producing better test scores in these students? Comparing reaction times against different conditions. Are they all producing that same average result, or is there at least one of them that's different? And so the way we measure this is with the variation known as between or within. Between is talking about the variation in the means overall. So suppose we have three groups, all approximately normal, with the following means and standard deviation of 3. So I have these groups. They each have their own mean, and they're all approximately normal, meaning they all have that same bell curve shape. When we sketch this picture, the standard deviation goes out to the inflection point. From the mean to where this changes curve was how far those went. So it's changing curve 3 away. So at about 53, the bell curve changes shape on both sides. I could barely do this when I was drawing it by hand. When I have 65, standard deviation of 3, at about 3 away, so 62 and 68, changing shape. They do continue out forever, so there is some overlap, but not a ton. And then same with the 80 at about 77 and at about 83. We have 68% falling between 47 and 53. We have 68% of the data for the 65, meaning falling between 62 and 68. And so on. There's not a lot of overlap, but there is still some. But that not a lot of overlap is the within variation. We're looking for if the within variation causes there essentially to be more overlap between these groups. Because when there's not a lot of overlap, they are clearly distinct. Their means are clearly different. We clearly have a group with a mean of 50. We clearly have a group of a mean of 65. We clearly have a group of 80 with a mean of 80. What if we extended those standard deviations out to 12? Same means, but what if they extended out to 12? So we have that 50, that 65, and that 80. Again, 12 is representing that change of curve point. So from 50 our mean of 50, 68% of the data will fall between what two values? What's the 68% part of the 68? Yeah.
38 to 62.
38 to 62. So a lot of the data, it's a lot more spread out in our bell curve. 65, what would that 68% be falling between? 68% of the data for our 65 mean group will fall between what two values?
53 and 77.
Yeah, 53 and 77. Getting a lot more overlap. Those should be the same height, but they are not. And then 80, same thing. 68% is falling between. I'm going to make that shorter. 68% is falling between 68 and 92. I saw a hand go up back there. Is there an actual question or? No? Okay. I thought I saw your hand. They're overlapping a lot more. The standard deviation is representing there is this random error, this random spread, this random variation inside each of these groups. And so now if I were to take samples, when I take samples, the chance of them overlapping and having sample means that are similar is a lot higher. And so it becomes a lot harder to see a distinction. It becomes a lot harder for there to be significant evidence that those means are different. And so the between variation, the variation between the 50, the 65, and the 80 stayed the same, but the error variation was a lot larger in the second, making it, if I took samples, a lot less likely for us to see that statistical difference between them. And then last example, approximately normal with given means. I wanted to change the means here. Mu1 is 62. Mu2 is 65. And mu3 is 68. So we have 62, 65, and 68. For standard deviations of 3, 68% of the data for the 62 will fall between what two values? 68 will fall between 59 and 65. My change of curve isn't until that 65. 65 will be between the 68% of the data for my 65 group will be between 62 and 68. There's a lot of overlap. And the 68 will fall between the 65 and the 68. Or, sorry, 91. There's a lot of overlap in those bell curves. Even though the between group variation has gotten a lot smaller. Actually, I shouldn't say even though. Part of the fact that the between group has gotten a lot smaller, there's a lot more overlap. Even though back here, when we had the standard deviation of 3, there's basically no overlap. So it's comparing that how close are the means together, along with how spread, how far variant are the groups, comparing those two spread of the means versus spread of the groups, and it's comparing those against each other to figure out, could these means actually be the same, or is one of them different? And so in our F statistics, when it's spread out a lot, this is talking about a large between group. Variates, and we'll define these a little bit more. But large between group divided by a small within. When I have a large number divided by a small number, I get a large number back. I get something very big. If I were to divide large over small, I'd get a big number back. At least a number significantly bigger than 1. So this is our F statistic. We get a large F value. And when we get large F value from our other stuff, large F goes with what size of a p-value? A small p-value. And small p-values say reject the null hypothesis. Our null hypothesis is not all the means are equal. Not all means equal. At least one mean is different. This would likely give a significant ANOVA F test, a significant result. Here, the between stayed the same. We still had a large between, but what changed?
The within.
The within. The standard deviation got a lot bigger. So we had large between divided by large within. And when I have two numbers that are very similar together being divided, what number is that close to?
1.
1. This is approximately 1. When our F statistic was close to 1, what was the size of the p-value? A small p-value or a large p-value? Large p-value. Large p-value. What do we do with a large p-value? Fail to reject. All the population means could be equal. There is a lot of overlap. And last one. Here we had a small between, but we also had a small within. I'm not going to write it down, but it's the same idea. Small between divided by small within still results in a lot of overlap. Still gives us a value close to 1. Still leads to fail to reject our null hypothesis. The means would be the same. They are at least close enough that we don't know if the difference is due to random variation or something else. We can't tell if there is a statistically significant difference or if it's just come due to random variation. So ANOVA continues to split it into the two parts, between and within. This is that difference of what we knew before as the model, the variation that's explained by the model, and the variation that's not explained by the model. It's the same general breakdown. Explained by the different treatments, not explained by the different treatments. So, between group variation measures how far the group means are from the overall mean. And it is reflecting, it's telling us about the treatment effect. So how much is the treatment causing this variation? is the different medication being assigned for blood pressure affecting the variation? Or is this just random chance from the people it's being assigned to? Within is measuring the variability inside each group. So measures variability inside the group. We'll do an example of calculating each of these, but it doesn't have a nice formula. And what it reflects, or what it tells us about, is it's telling us about the random variation. The unexplained. So, like before, we have these two variations. The between group is SSG. Don't love the fact that we use G because they're both group, but I didn't name them. SSG, sum of squares of the groups versus sum of squares of the error. So it's still SSE for the error, the variation one, and group versus model. So what our model one is reflecting the same idea as the sum of squares of the group. So key identity about them, the total is the sum of the group and the error. So the total sum of squares is the sum of squares of the group plus the sum of squares of the error. Just like the total variation in linear regression was the sum of squares of the model plus the sum of squares of the error. The total variation is the explained plus the unexplained. Each piece has their own degrees of freedom. Ultimately, the total is our number of people sampled, total minus 1. So that should be familiar. Our overarching sample size minus 1. Between group is N sorry, I flipped to the wrong spot and was about to read the wrong one. K minus 1. And the within group is N minus K. All right, if I take N minus K plus K minus 1, I get N minus 1. What K represents in this case? When we added it in on Tuesday, we added in this P. What did the P represent on Tuesday?
How many input variables?
How many input variables? Same type of idea. K is representing how many treatment groups. And there's a mean square. The mean square is the sum of squares divided by their degrees of freedom. So the mean square for between group, MSG, is SSG divided by the degrees of freedom for the between group. Call this DFG. And the within group is MSE, the error, is the sum of squares of the error divided by the degrees of freedom of the error. So this is degrees of freedom, the error. And then the F statistic is the variation between groups divided by the variation within groups. Same thing, MSG divided by MSE. We had before MSM, the model divided by the error. Now it's the variation between the groups divided by the error. And once again, we have an ANOVA table that we can fill in that works as we move across until we get to our F statistic. If F is close to 1, we fail to reject the null hypothesis. If F is much bigger than 1, then we reject. There are some conditions for the one-way ANOVA F test. We want it to be independent. There's random sampling / assignment. We are not specifically putting certain people into certain groups, but we are randomly assigning them to their different groups. There is normality. Each group is approximately normal. Maybe not perfectly, but approximately. And there is equal variance, or approximately equal variance. The standard deviation between the two groups is roughly the same across the group. So standard deviation is roughly equal between the between the groups. So actually doing an example. From numbers, we have 3 study methods being researched. The scores for each study method are given below. Group A, 3 people in the group made 85, 88, and 90. Group B, the 3 people in that group, 78, 82, and 80. And group C, 92, 94, and 96. 1, we want to compute the means for each group and the overall mean. So what is, or how would I find group A's mean? How do I find the mean for group A? Or somebody find it.
Is 87.6 repeat?
87.6 repeating. All right, as 87.67. What about group B's mean? This one we might be able to read off if you pay attention to what those scores are. Hmm? 80. And group C, same thing. Should be able to see it. 94. What we're doing naturally is adding the 3 scores in the group and dividing by 3. Okay, so then the overall mean. So if I took all 9 scores and found the mean of all 9 scores, what's the mean of all 9 scores? Hmm?
87.223 repeat over the 3.
Yeah. Overall, 87.22. The between group variation is measuring how much these means vary from the overall mean. So there's a formula for this, but overall what it is asking about is how much do these vary from the overall mean. The N1, or that should be an NI. NI is referring to how many are in each group. In this case, how many are in each group? 3. There's 3 in each group. And then we'll take our average from the group minus the average overall and square that and sum those 3 up together. So we'd have for group 3 times 87.67 minus 87.22 squared. This would be the variation from group A to the mean. Variation from group B to the mean. What would that look like? The 80 minus 87.22 squared. And group C to the mean. Is 80 minus 87.22 squared.
Isn't it 94?
Sorry. Yes, it is. Absolutely. I wrote them in my notes backwards. And so I looked at the third one and wrote the third one. But yes, thank you. When we actually calculate this out, should be approximately 295.03. It is just putting it into our calculators and evaluating that. But there is this formula, size of the group times that mean of group minus overall mean squared. Kind of like chi-squared of adding them all up. This is the sum of squares between the groups. So this is SSG. We want to compute the within, and this is now computing the variation inside each group and adding that up. So variation within each group is going to be adding each observation inside the group minus the mean of that group squared. So for group A, what were the 3 observations in group A and what was the mean? 85, 88, and 90, and its mean, group A's mean, 87.67. So we are going to take the subtraction of each of these, 85 minus 87.67, square it, plus 88 minus 87.67, square that, plus 90 minus 87.67, and square that. And we don't need to multiply by that 3 because we're looking at 1 observation each. That should calculate out to be about 12.67. Group B, our 3 scores were 78, 82, and 80. What was the average for group B?
80.
80. And so take each of these subtractions and square. $78 minus 80 squared plus 82 minus 80 squared plus 80 minus 80 squared. Without decimals, this one can possibly be figured out without calculator / even writing anything else down. What does that one calculate out to? 8. And we've got a 4 plus 4 plus 0. And group C, same thing. We have 92, 94, and 96. Anyone with number sense have a guess as to what that one's going to be? Also 8. It's the exact same setup, but I'll write it out. That we have 92 minus 94. Hey, that's also 2 squared. Plus 94 minus 94 squared. That one's our 0. Plus 96 minus 94 squared. Ooh, yikes. Is 8 again. And so the sum of squares within is adding those three numbers together. The 12.67 plus 8 plus 8, which their sum of squares within will be 28.67 from adding those all up. Okay. Finding our degrees of freedom. How many total observations were there? 9. So what's the total degrees of freedom? 9 minus 1, or 8. I like to calculate that one to check my work. I mean, it's important overall, but that one helps when we have between, within, making sure they add up. So between, so I called that DFG. Between is what formula? How do we find the between? K minus 1. K is? Yes, it is 3. What is K representing? Treatment, number of groups. So this one is one where you might be able to guess as to what K is and still get it right. It is the number of treatments, not the number inside each. So number of treatments was 3. So K minus 1 or 3 minus 1, which is 2. And the degrees of freedom for the error. How do we find the degrees of freedom for the error?
N minus K.
N minus K, total minus the number of groups. We had a total of 9 and 3 groups. 9 minus 3 is 6. 2 and 6 do add to 8. So our degrees of freedom work out. How do we find mean squares?
The sum of squares divided by degrees of freedom.
Sum of squares divided by degrees of freedom. So the mean square of the group what is the sum of squares for the group?
That was the 12 point, I think. Oh no, that was 295.
Yeah. 12 point was our first calculation in the next thing. 295.03 divided by its degrees of freedom, 2, is 147.52. Mean square of the error. What was our mean square? Our sum of squares for the error.
The 28.67.
28.67 divided by 6 is our, should be 4.78. And then how do we find the F statistic?
The mean squares divided by each other.
Yes, 147 over 4 0.78. So MSG divided by MSE, 147.52. Someone calculate that one.
Thirty point eight.
30.8. Okay. A good question came up the other day of what classifies as large. And if we actually look at that table in the back of the book, try not to pull it up, but if we look in the back of the book, the smaller the degrees of freedom, there's some really large values for the F statistic. In the hundreds and maybe even thousands. They level out very quickly when we get to higher degrees of freedom. By very quickly, I mean by the time we're around here of these degrees of freedom, we almost reach the point where 10 is considered big. Sometimes even 5 is considered big. The immediate answer I had at that point was, I think, generally, as long as it's been over 5. But they are very dependent on degrees of freedom. But as long as our degrees of freedom aren't 3 or smaller, we're probably going to get that 30 is considered big. 30 is considered big here. But one, I will make sure if I ever need you guys to find a p-value, give enough of that table for you to figure out if our F statistic could be considered big. But we'll work through actually finding it with a calculator real fast. With a calculator, we have second distribution, FCDF. What would be our lower and upper? Talk through it.
30.8 and.
Yeah, 30.8 for us is always going to be our lower, or not 30.8 specifically, but our lower will be our F statistic. Our upper will be infinity. E99. What were the degrees of freedom for the numerator? And why the calculator uses this phrasing, why the table does, is because it's not always the same. Yes. So the degrees of freedom for the numerator is our mean squares of the group, or mean squares of between. The degrees of freedom for the denominator, 6. If you don't have a calculator that types it out nicely, this is what it would look like following down that path. And we get 0.0006. We get something very small. So we get a very small p-value. So F is large. P-value is quite small. P-value was 0.0006. So what conclusion could we make about these groups.
Significant evidence.
Significant evidence of what?
Difference in study methods.
The difference in the means, yes. So there is significant evidence. Are they all different?
At least one.
At least one of them is different. So we have not found which one is different. We have found that there is one that's different. So significant evidence that at least one study method mean is different. There are then follow-up tests that could be done to figure it out. We could do some pairwise t-tests to determine which one is different. The t-tests being what we talked about in chapter 7 with comparing two means. So there are some pairwise t-tests we could do to figure out which one's different. There are also other tests talked about in the book. Again, we're on basically our last day of class, so not going to get into the details of those, but there is a test of Tukey's test. And there was another one talked about that I didn't write down. I guess that one didn't talk about. Yeah. We could do some different tests to figure out which one is different. There are follow-up methods, but we have at least come to the conclusion at least one is different. So, ANOVA tells us, or interpreting results, if F is large, there is strong evidence against the null hypothesis, giving an evidence of difference. If F is approximately 1, that means the groups are similar. So, what I was saying before. ANOVA tells us at least one mean is different. It does not tell us which mean. After rejecting the null hypothesis, there are tests that could be done. Namely, Tukey's test or pairwise t-tests. So, largely, ANOVA is telling us there is a difference, not which one. Similar to the multiple regression, it told us at least one of them is affecting the relationship. One of them is affecting the output variable. It doesn't tell us which one is affecting it. That's where we then turn to t-tests to figure out which one is affecting. But ANOVA overall is just saying, is there a difference? Is there an effect? So the connection to regression then, one-way ANOVA, which we are talking about today, is a special case of regression. It basically is saying our categorical predictor, the treatment, is acting like a dummy input variable. Instead of having a whole range of X values, we just have treatment 1, treatment 2, and treatment 3. Our categorical predictor is acting as a dummy treatment variable, input variable, and then the F test is giving us the overall regression significance test. And like with regression, there is this coefficient of determination. It gives the proportion of variation explained by the group means. R squared is the sum of the explained divided by the sum of the total. So SSG over SST, before it was SSM over SST. And it is giving us that percent of variation, or it gives us a decimal. So it gives us the proportion of variation explained by the group means. So we've calculated that before and said, oh, we get a 0.62. This is saying 62% of the variation is explained by the treatment. This would be saying so much percent of the variation is explained by the difference in the group means overall. So I'm looking at an example. The engineering team is testing 3 different manufacturing processes for producing a metal component. They measure yield strength in MPa for a part produced by each process. We're given these 3 processes, but that's not going to be the important part of these questions. Important part is going to be the environments. In the first environment, there is high precision manufacturing. The standard deviation for the parts produced in this environment is 5. The manufacturing process is highly controlled. In the second environment, there's a lot more variability. It's not as controlled. The standard deviation is 25. There is substantial variability in the production due to temperature fluctuations, material inconsistencies, and machine wear. Which population, if we were to run an F test, would it be more likely for us to get a significant F test? Which one do you think is more likely for us to get a significant F test?
Process C.
Oh, environment. So environment 1 or environment 2. Because these, again, the ANOVA F test is not going to tell us which are different. It's just going to say if they are different. So it's going to be the environment that tells us, that's controlling whether we're going to get a significant F test. So the question is, which environment would be more likely to get that significant F test? If we were to calculate these things, what is the environment controlling? Is it controlling the let me back up to a different question. these are the same outputs, the same mean strengths, no matter which environment they're in. Okay, so though process A, process B, and process C are the same, no matter which environment.
It would be the first environment.
Okay, why would it be the first environment?
There's a smaller standard deviation, so there's less chance of overlap.
Smaller standard deviation, less chance of overlap. What this example is going back to is where we first started with these pictures. Our example here about the manufacturing process could be changed to say we have this, let me get the numbers right. We have the 200 mean, we have the 220 mean, and we have the 240 mean. But in environment number 1, there's not a lot of spread. In environment number 1, there is consistent production and the standard deviation was only 5. We have a large between group, but the small within. There's not a lot of overlap. That produces a significant F test if F is large enough. What changed was in the uncontrolled environment, the spread was greater. And so there was more overlap. It was 200, 220, and 240. More overlap because the standard deviation was 25 instead. When the environment isn't as controlled, those fluctuations are bigger and there is more chance of error. There is more chance of variation due to error, larger denominators, larger within. So in our example, the second environment says there's more chances of error. That more chance of error gives a smaller F value and less chance for us to actually see the difference in the production. In which population does the manufacturing process explain more of the variation in strength? I'll scroll down. In which population does the manufacturing process explain more variation in strength? The one where the one where the environment's controlled or the one where it's not a very controlled environment?
So,
Controlled. Why? Yeah, their error is talking about it more. What also is happening here, there's a larger R squared ultimately. There's a larger sum of square of within, sum of square of between divided by sum of square of total. That R squared is larger, that proportion is bigger. So answering these, both of them are the first population. The variation within is small. Whereas the variation between stays the same. uh, I will say same divided by small gives a bigger value. If that denominator is smaller, gives that bigger F statistic, and the F statistic gives a smaller p-value. In the population, again, the first one, more error is it coming in the second one. So population 1, the process type explains a larger proportion of the total variation. So when the process type explains a larger proportion of the total variation, that is having a larger R squared. And so that first population, the better one for trying to find a difference between the mean strengths. That is where this section, or that was where planning to end this section. Tuesday, just announcement wise, again, lost it. You have a post-class activity due today from chapter 11. You have one due Tuesday. My plan, one, if there are any questions and anything you want to look at Tuesday, for sure come with those types of questions. Also, I am gonna plan on, I have one more at least chapter 12 example that I want us to look at. I just don't want to try and squeeze it in, but I want to look at one more chapter 12 example, and I will try to plan on also bringing an example to remind us of how previous stuff worked, like chapter 9 of chi-square. So look at, actually take some time to practice a chapter 9 example and a chapter 12 example of filling out that ANOVA. But of course, first and foremost, if you have questions you want to come with for reviewing, please do. And post-class activity due today, post-class activity due Tuesday. Homework 6 is due Tuesday. And then last exam is a week from today. Any questions on anything? All right. A little bit early. Have a great few days. And a great weekend. See you Tuesday for review.
Okay, for chapter 11,
Mm-hmm.
question 11,
Okay.
what test are you supposed to use?
Let me